So in this video, we're going to go over epoxides. Epoxides are three-membered rings where one of the members is an oxygen, okay? So we have two carbons here. The three members are 1, 2, 3, okay? That's where the whole three-membered ring comes from. They're not three carbon rings, they're three-membered rings. And epoxides, unlike regular ethers, are a group, right? An ether just stuck between, an oxygen just stuck between two R groups is an ether. These aren't that reactive, not that reactive. But epoxides are very reactive. So what makes them so reactive? Well, think about the structure of an epoxide. What shape do you see here? Well, I obviously see a triangle. I assume you do too. What's the total angles in a triangle? It should be 180, right, from basic geometry. So each of these angles is 60. But obviously, I haven't drawn them in here. But we have these carbons here. I mean, these hydrogens here, right? These are bonded. So this carbon right over here is bonded to 4 different things, which would make it a what kind of a carbon? That should make it a sp3 carbon, right? And what's the ideal angle for sp3 carbons? It's 109.5, right? We've learned that. That's the most stable angle it can be at, a tetrahedral, right? So if we have like this sort of shape, let's say we have methane with just 4 hydrogens. This is the most stable angle with 109.5 here. But over here we have 60 degrees. That is an insane strain caused by those angles. That carbon-oxygen bond does not want to be in that position. So you can almost think about why epoxides are reactive as in, you can think about the reason why epoxides are so reactive from the viewpoint of springs. Or you can imagine this is what it used to look like, right? Let's say you have a carbon here. Let's say like something like this, let's say a hydrogen, and you physically grab these two from here, and you just push them together. You push them together to form this, right? This bond right here, and I'll draw it in blue, is now this bond, and this one in green is now this bond. You've literally pushed them together, and just like any spring, you have some energy there that wants to free up. You want a more stable angle, so they always want to pop out, right? And the only way you can pop it out is by breaking these angles. Boom, it would pop out this way, or boom, it would pop out this way, right? So that's what that's the reason why epoxides are so reactive. You can think of it like that, as two springs that just really want to pop out on either side, okay? So let's go ahead and go over the different types of ways that epoxides react. So let me just grab this over here and move it up a little bit. Okay, so epoxides can react in 2 separate conditions. They can react under acidic or basic. And by basic we mean a nucleophilic condition. And that just means a nucleophile attacks it. Nucleophiles usually have negative charges, at least strong ones do, which would make it also basic. Remember, basicity and nucleophilicity correlate pretty well together. So let's go over both these conditions really quickly, okay? First, we're going to go over the basic conditions. Basic conditions. So I'm just going to go ahead and draw a very simple. Let me just make my screen a little bigger. Let me just scroll down. Okay, basic conditions. Here, let me just draw a simple ether, epoxide, sorry. Just the one I drew earlier. Don't mind my poor handwriting. Still trying to get used to this tablet. Okay, so we have this simple ether, and say we react it with NaSMe and DMSO. Oops. DMSO and also H2O. This is the first step, and then after that's done, we add H2O. Okay, so what's going to happen here? So this is going to follow a basic SN2 mechanism. We have a aprotic solvent. We have a strong nucleophile. Don't forget, we have Na plus and SMe minus. Remember the trick that you can always use: if you see an Na something, the Na definitely has a plus charge, +1 charge. So the other thing must have a negative charge, meaning it's probably pretty strong of a nucleophile. So this looks like it's going to be an SN2 type reaction, right? So what's the first thing that's going to happen? One of these bonds is going to break, either this one or this one. We don't know which one, and in this case, they're both identical bonds, so we can just break either one. This oxygen, remember the whole spring opening up, is going to break this bond by taking its electrons to it, right? It's going to take its electrons towards it. Let me just go down here. It's going to form this. It already had two, right? It had two over here. Now it has this new pair. I'll draw it in red, coming from those electrons, right? That bond opened up, and now we have a partial positive over here, right? And with two hydrogens coming off of it. This one, nothing happened to this one over here. Then our SME comes and attacks it with those lone pairs on the sulfur. And we end up with our final product, which looks something like this. Well, actually, that's not our final product. Let's go to our next step. Now we have an oxygen with a negative charge, right? You have 1, 2, 3, 4, 5, 6, 7. Right, 7. Oxygen has 6 valence electrons, 6 minus 7, you get a -1 formal charge. And then, let me just keep drawing in those electrons. 3 pairs of electrons. And then this sulfur, we still have 2 carbons, right? 1, 2, 1, 2. Our original number was 2. We haven't added any, so we still have 2. Attached to this SME, S-methyl group. You can draw it however you'd like. And then this water obviously serves a purpose. Notice how earlier I kind of forgot about it. I almost went to the final product, but don't forget, we're adding water for a reason. This negative charge isn't exactly stable. Obviously, even though it's oxygen, it can carry its electronegativity, its electrons fairly well. It still wants to have a neutral charge. So the next thing that's going to happen is this water molecule is going to come over here, and this pair of electrons, or any of the pairs, of course, are going to attack one of the hydrogens. It's going to pull that off of the H2O, and you're going to end up with SME, carbon, carbon, and an OH. So this will be our final product, okay? After a basic attack, okay? Right? That's pretty simple. Then the question is, what if our original epoxide didn't look like this, right? Notice how these two are identical sides. What if we had an epoxide that looked more like this? These are 2 methyl groups, they're not hydrogens, okay? Now we have 2 carbons that we can choose from to attack, right? Do we break, or another way of saying that is, do we break this bond or do we break this bond? Okay, so in this case, we always, this pen is getting kind of annoying. We always attack the less substituted carbon under basic conditions, okay? This same principle does not, and I repeat, does not hold true for acidic conditions, okay? So let's go over what this is going to look like. Similar mechanism. Triangle, right, with an epoxide. We have the nucleophile. It's going to attack either here or it's going to attack here. Either, of course, after the bond breaks. And in this case, it's going to attack right here, not this one right here, okay? So what we're going to end up with is, a very similar thing. Let's say we use NaSMe and DMSO, and then H2O. You're going to get the same thing. You're going to get an alcohol. You're going to get this. These are those 2 methyl groups right here, okay? And you're going to have the SME over here, right? Cool. This should be a straight line, actually, if we get our carbons right. SME. Okay, so this should be your final product. Now we're going to move on to the acidic conditions. Okay, so for the acidic conditions, our reactions are going to look something like this. It's kind of similar, but not exactly the same. Okay, I really got to get used to drawing these. Let me just fix my tablet for a second and see if I can draw these any better. Okay, Still got to get used to that, but that's all right. Okay, so similar compound. These two carbons are not identical this time, but this time we're gonna react this with a acidic condition, right? Like H2SO4, and let's have a weak nucleophile. Doesn't really matter since it's pretty weak here. Okay, weak nucleophile. We want it to be a weak nucleophile because we don't want this fairly acidic compound to react with a fairly basic strong base, let's say, because then these two would react too often and then it wouldn't really help us in our actual reaction. Okay, so in this case we have this acid with this weak base. The first thing that's going to happen actually in this acidic mechanism, condition/mechanism, let's say, is this oxygen up here is going to be protonated first, right? So this H2SO4 is going to be protonated by one of these lone pairs. It's going to take that hydrogen, and you're going to end up with an OH with a positive charge, right? And we're, again, positive charge because 1, 2, 3, right? Lone pair over here, 1, 2, 3, 4, 5 bonds / lone pairs to oxygen. 6 minus 5 is +1, so +1 charge. Okay, now we're going to think about which bond is going to be broken in this case. Is it going to be this bond or is it going to be that bond? Now in this case, under acidic conditions, we're going to break the bond on the more substituted carbon. And the reason for that is because once it is broken, I'm going to go over the individual nitpicky steps after breaking this bond right here, okay? What would happen? You'd have this, right, neutral. Then you'd have this. You have those two things coming off of it, a positive charge. If I drew the same thing for the opposite case, it would look like this. It would look like OH, boom, boom, and then you'd have this with obviously 2 H's coming off of it only, and you have a positive charge. Which of these positive charges, this one or this one, is more stable? Well, if we've learned anything so far in this class, it's that a more substituted carbon is more stable, right? Due to things like hyperconjugation. So this is a tertiary carbon, right? This carbon is attached to 1, 2, 3 carbons. This carbon is attached to only one carbon. This is primary, this is tertiary. This carbon is much more stable, right? When the carbocations form. This is before the methanol comes and attacks it. This is more similar to an SN1 mechanism than the previous basic condition, where it was acting more like a SN2. But it's not a complete SN1 mechanism because the stereochemistry matters in both conditions. I'll go over that in a little bit. But just think about the fact that this is kind of similar to an SN1 mechanism. First the carbocation forms and the stability matters. Okay? So let's go ahead and go over what happens next. We can draw this right here. This is going to come, this carbocation is going to be attacked by our very weak nucleophile. Again, just to show the electron movement. This is really helpful, by the way, to draw electron movement because it just kind of helps solidify things and make them more sense. Make them make more sense, I guess you could say. All right, here's this OH. We're going to have this carbon over here with those two other carbons. You're going to have this OH, methanol, not methanol, methyl. This oxygen, however, is still a positive charge because of that OH, but we can have another methanol come in, and we've seen this multiple times, and take that hydrogen off, and this will just produce methanol OH2 positive, which is just going to be in our solution, and our final product looks like this. Right, we formed an ether. Okay, so this is our final product under acidic conditions. But the key takeaways here are that under basic conditions, we attack the less substituted and under acidic conditions, we attack the more substituted one. Okay? Yeah. This is the thing. And we always need a weak nucleophile for the acidic conditions The nucleophile strength really doesn't matter. Weak nucleophile is good. And here we want, of course, a strong nucleophile. And the stereochemistry, which I'll go over right now. Stereo. Better yet, we have an inversion in the stereochemistry for both. For both cases. Okay, and I'm gonna go over an example of that right now. So let's go over this example of an acidic condition. Wow, that is a terrible drawing. Let's draw that again. I wonder why it's so hard to draw a triangle. Okay, not bad. Could be better. Let's draw that. Let's draw a wedge over here. And then let's just draw that. Okay, this is going to react under HBr, right? It's a strongish acid, strong acid. Nonetheless, it's an acid. And we're going to react that. So which carbon is this going to attack? Remember, we learned that under acidic conditions, we usually attack, not usually, we always attack the more substituted carbon, which would be this one. This one's a primary carbon. This one is a 1, 2, 3 tertiary carbon. This one's tertiary. This one's primary. Okay, so what's going to happen? We're going to first protonate, right? That's the first step. We got to first protonate this oxygen over here, which gives us a OH, positive charge. This stays the same. This, right? Then the next step is going to be for us to break that bond right here. We're going to break this bond. It's going to get pulled up to that oxygen. That's going to form this, right? Then this carbon right here looks like this with a wedge. And here, remember, after this HBr gave its H away, we have some bromine ions in the solution, right? So if I draw the bromine in blue, it looks like this. And again, we're always going to have a backside attack, right? So this bond up here broke. Let me just make sure I put this positive charge in, just to make it clear that we're attacking this carbon. You're going to have these lone pairs on this bromine come and attack from the back side, right? This carbon over here. And this is going to lead to an inversion in the stereochemistry. So actually, to show this really, really well, let's first identify what kind of a configuration this molecule had in the beginning. Was it an R or was it an S configuration? So remember, we're gonna put our lowest priority group, which in this case would be, let's see, we have carbon, carbon, a carbon, an oxygen. This is obviously our first most important group. Let me do this in green. This is our most important group, 1. Our second most important group is this 2 carbon thing, because remember this is attached to a carbon, hydrogen, 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 carbon, oxygen. That's pretty important. And then this one's a carbon to a carbon. So carbon to a hydrogen seems like it's our lowest. And then between these, carbon to oxygen, then carbon to carbon, this is number 2, and this is number 3. So if we put our lowest priority group, the 4, in the very, very back, right? Then we would have what kind of configuration? We'd have 1, 2, 3. This is an S configuration, right? So our final product should be an R configuration. Now the way you draw it kind of completely depends on you actually, but I'm going to draw it in the way I think is easiest. We're going to have these stay the same, just for, for the sake of it being easy. Let me draw it a little higher. We're going to have this over here, and we're going to put the BR over here. Okay. There's another way you can draw the stereochemistry, which, I'll just add a little extra part to the end of this video for you guys to see how else you could have drawn it, but you guys can play with that and you'll figure it out. So for this one, the stereochemistry is now what configuration? Let's test it out. Let's just check real quick. This is a carbon, carbon, bromine. That's number 1, of course. It's the most important. And this is also a carbon. So carbon, 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 bromine. Bromine wins. Then the next important one, carbon, carbon, carbon. This carbon is attached to an oxygen. That one's attached to 3 hydrogens. And that one's attached to another carbon. So this one's number 2. Now number 3, carbon to carbon, carbon to all hydrogens. This one's number 3, of course. And this one's number 4. Let me just draw 3 a little better. 3 and 4. So again, Putting our lowest priority group in the back over here, we see that we now have a what configuration? We have 1, 2, 3. This should be an R configuration. Notice how this was an S configuration. That looks like a 5, but that should be an S. That's way too coincidental. Let's draw a nice loopy S. That's an S configuration. This is an R configuration. We see that we inverted the stereochemistry. This is the correct structure right here. Okay? And we followed all the rules. We attacked the more substituted carbon. This was a good reaction for the acidic condition. Okay, that should be it for now. Thanks for watching, guys. So a little earlier, I mentioned how you could do this stereochemistry again, but in a better way. I mean, in a different way. I think this is the best way, but you could also do it this way, just so you can see the difference. You could also draw it like this. So say this goes straight along, and then notice how this one was originally a dash. We can now draw that as a wedge, like that, right? It's a carbon, it's a methyl group. And then over here, instead of a wedge, we can now draw a dash. And then instead of putting the BR here, we can put the BR up here. And now this one's a bit harder to see, but it's still now going from an S to an R configuration. Because if we name our priority groups again, one last time, this is of course 1, because bromine is the biggest of them all, or the most important of them all. Then we have the second one being this one over here. Then we have the third one over here, and the fourth one over here. If we put this in the back of the paper, right now this is coming towards us. So if you can actually imagine it going back into the paper, you'd be looking at this as 1, 2, 3. If you kind of tilt your head and imagine looking at it from the back, it's actually going in clockwise direction, right? Like this, from the other side of the screen, or from the other side of a paper, right? So that's why this is also going to be our configuration. I think this was a bit harder. You can just keep the dashes and the wedges the same as the original, and just instead of putting the next object up here like this one, you'd put it on this side, on the opposite side of this bond right here, and that way you still get R. Either way, honestly, I think the best way to think about this is just playing around with it. Do it yourself, draw it, do the hole, putting it behind the paper, lowest functional group, rose petal, whatever method you have for R and S, no matter how you do it, just go ahead and do that and you'll figure it out. Okay?